Welcome to Wildcat Science with Mrs. Helgo. This is Chemistry, Chapter 11, Section 3, Part 6. And last time we were talking about limiting reagents, and we did a problem involving iron and water to make black iron oxide to give off hydrogen gas. And we calculated the limiting reactant by figuring out how many moles of each reactant we have and calculating if that much of one reactant reacted, how much of the other one would we need. And we did that twice, and that was our need. And then we compared those two moles, those two sets of moles, and we figured out water. We didn't have enough water, so water is the limiting reactant. So now let's look at B. How much of the excess reagent or reactant is used? Well, if we use up 1.998 moles of water, we're going to need 1.499 moles of iron. And so we're using up all the water to use up that much amount of iron, so that's the amount of iron we're going to use. So 1.499 moles of iron. But they probably want that in grams. So let's do a mole to gram, a mole to mass conversion. So I'm going to start out with 1.499 moles iron over 1 times, just double check we've got that right, and I'm doing grams on the top and then moles on the bottom. 1 mole iron. And then we know our molar mass is going to go on the top, which I believe is 55.85. Great. 55.85 grams Fe. Our units cancel. And then you want to do this calculation and figure out the grams of iron. Okay, did you get your answer? So I got 83.719. If I look all the way back up into the problem, I have 167 grams of iron, which is 3 sig figs. So for this one, I'm going to limit myself to 3 sig figs. So 83.7 grams of iron. Did you get that? If so, great. All right, please write this down. To find the amount of product formed, you must use the limiting reactant. So if you just pick one of them and you pick the wrong one, you're not going to get the right amount of product. Because if we're looking up here, if we were to use 2.99 moles of iron, to form how much product I'm going to form, not all of that product's going to form because not all of the iron gets used up. The water runs out first, so that determines how much product we can make. So always pick the limiting reactant to determine the amount of product. So I've already converted the water that I have, and that's what I'm going to do. I can only work with what I have. So I'm going to take the amount of water that I have, which is in moles, and do a mole to mass problem and figure out the amount of product. So I have 1.998 moles water. Okay, so I know that I have 1.998 moles of water. We could write the original quantity, 36.0 grams of water, but then we'd have to do our mass to mole conversion, which we've already done. And I'm trying to find the amount of product. So the grams of product, which is black iron oxide. I believe that one is Fe3O4. Fe3O4. Okay, then we're going to calculate it, set up the problem, and calculate the moles of our known, which is 1.998 moles of water, our limiting reagent, times our mole ratio. Well, moles of water are going to have to go on the bottom, so let's go back to our balanced chemical equation, which is actually all the way up here still. 4 moles of water and 1 mole of black iron oxide. So moles of water go on the bottom, 4 moles water over 1 mole Fe3O4. Okay, but that's not quite good enough because we want grams of the product. We want to know how much we're going to get. So, we know we're going to have to use molar mass. So moles go on the bottom so that we can cancel that, Fe3O4. And now you're going to have to calculate the molar mass of black iron oxide. So please take a minute and do that. Okay, did you get 231.55 grams Fe3O4? If so, good job. If not, I want you to run through it one more time. Alright, so moles of water cancel with moles of water. Moles of black iron oxide cancel with moles of iron oxide. And I'm left with grams of black iron oxide. So now we're going to run through this calculation, so please take a moment and do that. Okay, what did you get? I got 115.659. So if we remember, we had 3 sig figs on the water, 36.0. So we should have 3 sig figs on our answer. So 116 grams black iron oxide. Okay, let's do a check. So we already double checked that 36 is about 2 moles of water. So let's go up to our balanced chemical equation. If I have 2 moles of water, that's half of the balanced equation of 4. So that means I'll get about half of a mole of black iron oxide. And we figured out the molar mass of black iron oxide is about 230. About half of that would be about 116 grams. Did we get something close to that? We did. Did we answer the question? Well, let's double check. What is the mass of the product, black iron oxide? We did. Good job. Okay, let's take a look at some pictures. Okay, there's some nice pictures on page 349, some graphics. So, a limiting reactant, we have reactant A and we have reactant B. And B is the limiting reactant, so all of it gets used up. And then we have excess of our other reactant, and we get our product C. So here is another graphic, steps for determining the limiting reactant. Convert both of the reactant masses into moles. And that's how much you have. And then use the mole ratio from the balanced chemical equation to find how much you need of each reactant. And then compare the amounts of the reactants. Compare what you have to what you need. If what you need is more than what you have, it's the limiting reactant. So if you need more than you have, you don't have enough, it's the limiting reactant. So here's another graphic. We have our grams of reactant. Convert that to your moles of reactant, and then use the mole-to-mole ratio to figure out which one is the limiting reactant, and then to do that second part of the question, how much product is made. You have moles of limiting reactant, and you do a mole-to-mole problem, and then, a mole-to-mass problem to get the grams of the product. Okay, so let's talk about a certain type of process. The Haber-Bosch process was developed in World War I to make ammonia to use for explosives, and now we use this to make fertilizer. Making ammonia using the Haber-Bosch process uses a lot of energy and can be expensive. Worldwide consumption is about 150 to 200 million tons of synthetically made ammonia. So, what is the consequence for the environment of this? What is the consequence for underdeveloped countries? So I want you to take some time and to think about that, and we'll talk about that in class. Okay, now what you've been waiting for, it's your time. It's your time to give it a try, your time to shine. Okay, please write down this example. 100 grams of nitrogen reacts with 10 grams of hydrogen. Which reactant will limit the amount of ammonia produced? So remember, you're going to have to go through all the steps of writing a balanced chemical equation and figuring out your mass into moles, and then figuring out how much you have and then how much you need and which one's the limiting reactant. And then you're going to use the limiting reactant to find the amount of ammonia, to find the amount of the product. All right. Happy solving. I will see you later. Bye.